This section, section 19.3, is very brief, and we are here going to discuss what specific heat capacities we have for ideal gases. These gases are somewhat different. You'll recall that we had the equation that the change in heat of any substance was the specific heat times the change in temperature. Of course, this related the change in temperature to be related to the change in temperature to be related to the change in heat. There's also a mass term in here that appears to be missing here, so that should be a mass right here that I will correct. Because if we have twice as much mass, we have, of course, twice as much heat that's required for a given change in temperature. But for gases, we can say, what is this C? And there are four cases that we like to discuss. The first of these is at constant pressure. And the C for constant pressure for an ideal gas is always 5/2 of R. And this can actually be derived. This is a monatomic That means that there's a single atom, like a helium, ideal gas at constant pressure. Now, if we have constant volume, it turns out that the specific heat at constant volume is 3/2 R. And as I said before, both of these can be derived with a little bit of effort. If, however, and they relate to these 3/2 and the 5/2 relate to the degrees of freedom that exist within the gas. In fact, the 3 occurs because of the degrees of freedom of three-dimensional space. If we have a diatomic gas, then we have two atoms connected to each other, and this type of atom can also rotate or vibrate in addition to its normal translational motion, so therefore the specific heat is going to be different. And therefore, for the specific heat of a diatomic ideal gas, this constant pressure is here and constant volume is here. We again have two equations, one where Cp is 7/2 R, and the other is Cv, constant volume, which is 5/2 R. And you'll notice a common thread in all of these, and that is the fact that the Cp minus the Cv is equal to R. Is exactly 1 unit of R greater for the P, for the constant pressure, than for the constant volume, both if it's monatomic and if it's diatomic. And so this equation obtains. And these can be very useful in looking at these gases and not having to compute or write down elaborate tables for what the heat capacity is for constant pressure and constant volume. And so this replaces a tremendous amount of data, whereas we do not have a similar thing when we're dealing with solids and liquids. It's only with the ideal gases that we have this.